Good afternoon, everyone. Welcome to our third session of SOAP today, which is also the last session. 2 more hours. Let's survive for 2 more hours. And firstly, let's welcome our keynote speaker, Qirun Zhang from Georgia Institute of Technology. His research focused on programming languages, software engineering, and program analysis, which we all familiar with, I guess. He is going to present us this compiler-assisted translation validation. He will present recent advances in leveraging compiler-generated translation records to improve the scalability and the effectiveness of compiler correctness validation. Welcome. Thank you.
Thank you for the introduction. Hi, good afternoon, everyone. I'm Qirun Zhang, and I'm super happy to be here and to deliver the talk on compiler-assisted translation validation. So as you may notice that the main theme of the talk will be centered around the compilers. So let's talk about compilers first. So what is a compiler? Compiler is basically a computer program where it takes some text inputs and does some computation and produces its output. But compiler is a specialized program. It is actually a higher order program. In this case, the input to a compiler is another program P, and then the compiler will do the optimization and generate a optimized program, usually in a binary form. So compiler is actually so fundamental, and therefore compiler correctness is of paramount importance. And to ensure the compiler's correctness, and we have 2 kinds of approaches. In the first category, and then we can focus on reading about the internal behavior of compilers, which is referred to as compiler verification. So in this case, we just write the specification on the compiler and then prove that the compiler is correct by construction. For the second type of approach, we will be looking at the external behavior of the compilers, where we try to reason about we try to establish the relationship between the input and output programs, and therefore we prove that the compiler has done the right thing in order to optimize this particular program, which is usually referred to as translation validation, as well as compiler testing. So in the recent years, and we have observed a lot of success in the domain of compiler validation. Notably, Alive2 is the state-of-the-art SMT-based tool for compiler validation. So let's think about what we really want to achieve when we want to reason about the external behavior of compilers. So in this case, if we forget about the compilers, we are given 2 programs, P and P prime. So we want to prove that the 2 programs preserve certain properties, where the property could be like equivalence, like aliasing information, so on and so forth. And precisely, the problem statement is that given 2 programs, P and P prime, we want to prove that P and P prime hold certain properties phi, where phi could be like termination and aliasing and I/O equivalence. So this is like the traditional static analysis problem, right? We know that the problem is undecidable due to the right theorem. And usually, in many of static analysis papers, and we will say, okay, the problem is hard and it's undecidable, therefore we need to do like over approximations. And in practice, static analysis is super expensive. Therefore, usually we do lightweight dynamic analysis, which is called testing or validation. Okay, so let's think about how do we test a compiler? How do we test a normal program? Suppose that you have designed a calculator, you are very happy, and you want to validate that you have actually designed a calculator. What do? So you will generate a bunch of inputs, right, like 1 + 2, and then according to the specification, you will observe the output of your program. If it's 3, okay, you are good. And if you gave a set of inputs, therefore you can be assured that you have developed the correct program. Okay. Now let's shift the gears a little bit and talk about the compilers. Because compiler is a higher order program, the input to the compiler is yet another program. Without loss of generality, we assume that the input to the compiler for the scope of our talk is a calculator. And the compiler will perform code optimization and produce an optimized version of the calculator prime. So in this case, you have a bigger question to solve. Basically, how do you know that calculator prime is actually an improved version of your original calculator? Okay, so again, according to our previous slides, we know how to validate a calculator, which is straightforward. You just generate a bunch of inputs and observe the output. Okay, now let's put together everything. Our goal is to validate the correctness of the compiler, and to achieve that, we need to get some input program. In this case, it's a calculator, and we have obtained the optimized calculator, calculator prime, and we want to show that the two programs preserve certain properties. In order to achieve that, we need to generate input to both calculators and observe the output. If if they agree on a certain output and which is also consistent with our specification, then we know that at least in this case, the compiler is doing the right thing to optimize your program. Okay, so this is the traditional way to do the compiler validation, and there are two limitations with this workflow. The first one is the coverage. Because we are doing the dynamic analysis, so it is difficult to exhaustively generate all the test inputs to exercise the runtime behavior of a program. Therefore, it's harder to fully exercise the runtime behavior of the calculator. And recall that our end goal is to validate a compiler, and the calculator is just only one input to the compiler. Therefore, even if you achieve 100% state coverage and whatever coverage for the calculator, you still only achieve a relatively small coverage for the compiler, right? So this is one of the fundamental limitations with regard to compiler testing and also those testing-based validation techniques. The second limitation is that because it relies on dynamic analysis. Suppose once you have found a bug and you are very happy and you will call it a day, okay? But what after, you may also ask, once you have found a bug, and is it possible to kind of automatically find a patch to fix the bug? This is particularly important for compiler testing because if you go to GitHub and you may observe a lot of unresolved bug reports because compiler bugs are super hard to fix, and sometimes if you only report a bug, it is less efficient or less useful for the open source compiler community. Okay, so therefore we want to promote the concept, and we want to improve from purely compiler validation to compiler analysis. Okay, so our end goal is that we want to perform compiler testing and validation without the need to generate input to those testing programs. In this case, we still need an input program P, and we will be observing the output behavior of P prime. But we don't need input to these two programs in order to check that they are kind of equivalent or preserve certain properties. Okay, how is that possible? So let's revisit the entire compiler validation workflow. So the traditional view, in the traditional view, the central problem here is that we will treat the compiler as a black box. Usually we focus on validating the behavior of P and P prime, and we somehow we omit the fact that P prime is produced by a compiler. Okay, therefore we end up with this generic problem statement, like with P and P prime, we want to prove certain properties, and we all know that those are harder static analysis problems. Okay. Our new technical insight is that actually in the domain of compiler validation, we are tackling a simpler problem. In this case, we are not giving two arbitrary programs, especially P prime, right? So in this case, P prime is produced by a compiler, where a compiler is a deterministic algorithm, right? And if somehow you do some instrumentation of the compiler, you can exactly know what steps have been performed in order to produce this optimized program P prime. Okay. Therefore, the solo input to the entire validation framework is P itself, as opposed to P and P prime. Therefore, it will dramatically simplify the problem, and you don't need to worry about too much about the undecidability result, right? So we have a P, and we have a deterministic way to produce the output program P prime, and we want to check if P and P prime preserve certain properties. Okay. So this is the technical insight behind our compiler-assisted translation validation framework. Okay. In particular, we will instrument the compiler. Okay, usually we refer to LLVM because this is the widely used compiler in the industry and academia. So we instrument the compiler. Therefore, along with the optimizer program P prime, the compiler will also emit a sequence of actions taken to produce the optimized program P prime. And then we use this meta information to establish the mapping between P and P prime in order to help with the subsequent validation tasks. Okay, so this is the central idea behind our compiler-assisted translation validation framework. Okay, next I'm going to talk about two concrete examples to materialize the basic idea. This is our basic idea. Now we want to utilize the compiler internal information to improve the compiler reliability by performing the translation validation. Okay, so I will be talking about two client applications. One is related to debug information generation, and the other one is related to speeding up SMT-based translation validation tools. Okay, so let's first talk about debug information generation. This is like a published work at last year's PODI. First, a little bit background. And for optimizing compilers and the compiler, if you add this flag -G, usually the optimizing compiler will emit some meta information to your binary to facilitate the source code debugging activities. And in this case, you have an original program in source code, and you have optimized the program in binary. And if you use the -G, then the compiler will emit debugger information in the binary. Therefore, you can actually run the binary in a debugger, and then to debug your program. And you can basically stop at a certain location and then inspect the value of certain variables. Okay, so the debugger information is kind of meta information baked into your binary to establish the runtime relationship between program execution and your source code. Okay, there are two essential tasks in any debugging session. The first task is related to debugger location. So you first set up breakpoints, and then the debugger should be able to stop at a certain location. The second task is basically you want to inspect the value of the variable in order to debug. Okay, so in this talk, and we will be focusing on the first type of information, which is called the debugger location information. Okay, in particular, we want to basically ensure that the compiler, if you set a breakpoint at 7, we want to ensure that the debugger will actually stop at line 7 instead of line 4 and line 3. Okay, so this is the property that we want to validate. Okay, so this corresponds to the property phi. And let's take a deep look at this property. Okay, so suppose that in this case you have two programs, P and P prime, both in the binary form. P corresponds to the unoptimized program, where P prime corresponds to optimized program. Okay, suppose that in the unoptimized program you can stop at line 7. Is it always guaranteed that you can stop at line 7 in the optimized program? Probably not, right? Yes or no, right? So because the compiler optimization will do some source code rewriting, it will eliminate, for whatever reason, it will eliminate your instructions, or it will also do like people optimization, right? So it will reduce a chunk of code to a single instruction. Therefore, maybe there is no line 7 in the optimized program. Okay, so we put a question mark here. On the other hand, if we take a look at, we also take a look at the complement. Suppose in your original program, given a set of inputs, you cannot stop at line 5. It is always guaranteed that you cannot stop at line 5 in the optimized program based on the same set of inputs. This should be yes, right? Because, right, you cannot stop at line 5, and then in the optimized program, you should be, assuming that compiler is doing the right thing, right, you shouldn't magically be able to stop at line 5 with the same inputs, right? Okay, so based on these two claims, we can see that the debug location associated with the optimized program P prime is actually a refinement of the original program. That's basically the information that we want to, the formal property that we want to validate in our debugger information validation workflow. So we want to guarantee that the debugger location observable in the optimized program is only a subset of the debugger location observable in the original program. Okay, so in the past, how do we do it? This is a very traditional, like a standard testing problem, right? In order to make sure that one set is a subset of the other, what we do is that we have a program P, and we compile it, and we optimize it, and obtain P prime. And then this is testing, right? So we generate some random inputs, and then we run the program P. Seems that I don't have cursor. Do I have cursor? Okay. Yeah. So we run a program. We run a program in a debugger, and then we collect. Right. We set breakpoints, and therefore we can collect a set of locations that are stoppable in the original program. We do the same thing for the P prime optimized program, and we get a set of locations that can be stopped in the optimized program. And then we just compare the two sets and to make sure that one set is a subset of the other. Okay, this is the traditional like a compiler testing and validation workflow based on testing. And actually, we have done some early work in this direction, and we managed to find roughly like 70-ish bugs related to debugger location generation in optimizing compilers. Okay, but here in this talk, I want to mention that we can actually do one step further, and we can improve the workflow. So by utilizing compiler internal information, we actually do not need to generate. We do not need to generate inputs for P and P prime, and we can directly utilize debugger compiler internal knowledge to establish the mapping between P and P prime. Therefore, we can find the bugs in related to the debugger information generation. Okay, the technical insight, as I mentioned, is actually a realization of the general idea mentioned at the opening of my talk. So we want to instrument the compiler so that when the compiler produces the optimized binary P prime, it will also generate some meta information. In particular, we will be focusing on two types of information. The first type of information is called instruction manipulation operations. In this case, we want to basically we want to establish a mapping between an instruction in the source code in an unoptimized program and a destination instruction in the optimized program. The second type of operation is related to how compiler actually updates debugger location, because when you change an instruction in the source code, the compiler is supposed to update the debugger location as well. And then we can also instrument LLVM's source code to obtain such activities. Let's talk about these two types of information using a concrete example. This is maybe a minimal example to illustrate the idea. Okay, so here in the original program, we have this multiplication instruction, and this case reflects the traditional strength reduction optimization path, where we can sometimes replace an expensive multiplication instruction with addition. Okay, so the original multiplication instruction is at line 7, and the compiler will replace this instruction with a cheaper instruction, which is addition. The same instruction at line 7 in the optimized code. Okay, so we instrumented the compiler. Therefore, we know the source code, LLVM source code, to perform such kind of code updates. And by instrumenting those instruction manipulating operations, and we will be able to tell the source code instruction, the source instruction in unoptimized code, and the corresponding destination instruction as prime in the optimized code. This mapping is is important to establish to do the translation validation. Later on, we will see an example. Okay. Second type of information is called the debugger location update, because after optimizing this instruction, the compiler is also supposed to update the debugger meta information. Okay. In this case, we can basically instrument those debugger information updating APIs in LLVM. And in this case, we know that the compiler is performing something called preserving like operation on this in this case, right? Therefore, we know that what compiler does is preserving. Whether or not it's correct, we don't know, but we know that the compiler is preserving the debug information according to this case, okay? So the actual approach is a little bit more complicated, but I'm using a smaller example to demonstrate the basic idea. So this slide shows the majority of functions that we instrument in LLVM. In particular, for the first type of instructions, we will be tracking like 4 types of activities. And for each type of activity, we will basically establish the mapping between the source instruction and the destination instruction. And for debug location updates, basically we will, we will, according to the LLVM's source code debugging documentation, in the documentation it defined the 3 types of updates: preserving, merge, and dropping. And according to the 3 types of updates, and we kind of map those updates into the source code, and we find the specific API to perform this type of actions. Therefore, at the runtime, we will know what compiler does in order to optimize the debugging information. Okay, so to sum up, and by instrumenting the compiler, when the compiler produced the optimized program P prime, and then the compiler will also dump a set of actions like create, move, clone, so on and so forth, and then that's tell us that what compiler does in order to optimize to produce this optimized code. Okay, so at this point, we kind of did the instrumentation, so we know the compiler what the compiler does in order to produce the optimized program. But the big question is that we still don't know whether or not the compiler is doing the right thing, right? In order to answer this question, we need to actually perform additional analysis to tell us the ground truth, okay? So in this particular problem, the ground truth could be obtained by simple static analysis, okay? So recall, what we are trying to do is that we want to validate that one set is a subset of the other, okay? Basically, what we do here is that we can perform like control flow analysis on the original program and optimize the program by also tracking the internal representation of LLVM. Okay, we can traverse the control flow graph, and given a source instruction, and then we can traverse the control flow graph and obtain all paths that will go through this node. For each path, we will actually read the data structures from LLVM and obtain a set of debug locations associated with those paths. Therefore, we can, for a particular instruction, we can get a set of debug locations from the compiler's internal knowledge. Okay, right? So we can also do that for the destination-like instruction. Now, because we instrument the compiler, right? So we know the source destination mapping, during the process. Therefore, we have these 2 sets, right? Like with respect to only one instruction, the L source and the L destination. Then the remaining step is straightforward. We just compare these 2 sets and then to determine the expected updating behavior based on the information we collect. For example, the dropping, right? So the dropping rule is that if the debug location set is not a subset of the, if the debug location set in the optimized program is not a subset of the debug location set of the original instruction, therefore we need to drop the instruction. That implies, this implies, right, because it's not a subset, it implies that in the optimized program, maybe it's possible to stop at some locations that are not observable in the original program, right? So therefore, in order to preserve the correctness, the compiler should drop the debugging information with respect to this instruction to preserve the correctness. Okay, by dropping this. By dropping the debug location, when you actually debug the program, the debugger will show that the location has been optimized out. That's an expected behavior, but the debugger should never stop at a location that is not observable in the original program, right? So this is only one of the 3 rules. Basically, we can design the rules and prove the soundness of these rules, and therefore we can use this as a ground truth to tell us whether or not the compiler has done the right thing. Okay, to put everything together, in our new compiler-assisted translation validation work, and we will instrument the compiler. Therefore, the compiler will tell us like instruction manipulations. It will also tell us the debugger update options it has performed. Okay, with the help of the first type of information, we can tell the source instruction and the destination instruction. Then we perform a static analysis on the input program and output program, obtain a set like this debugger location set. And using these three rules, we can compute the ground truth, like the expected behavior of compilers with respect to a single instruction. And because we also record what the compiler does in order to optimize this program. And all we need to do is to compare these two options. If there's a discrepancy, we know that something is wrong in the compiler. If there's no discrepancy, we are good. Okay? So this is the basic workflow for the compiler-assisted translation validation process. Okay? So next, I'm gonna briefly talk about the evaluation results. One thing I really want to note is that by using this compiler-assisted framework, we can not only find the bugs, but we can also suggest a fix. Okay, that's something that hasn't been done before. So if you think about what we do here, what we do is that we track the execution of compilers, right? We know the ground truth. We know the correct update behavior of the compiler on this specific input. Therefore, if we find out that the compiler is doing the wrong operation to update the debugger information, we can locate that API and replace this incorrect API with the ground truth API, right? Recall that we only have 3 types of APIs. We can replace an incorrect API with a correct API. Therefore, we can actually fix the bug. Okay, so this is something that I'm very excited about. Like, we not only can find the bugs, we can also propose a fix. And this turns out to be very valuable for open source, like for compiler developers. Okay, so using our compiler validation framework, and we have reported roughly like 46-ish bugs to the LLVM developers. And unlike anything before, we also propose 46 patches to the developers. And all of the patches are accepted by the LLVM developers. And that shows that our work can actually solve the real world problem, and it can really improve the efficiency of the debugger information updates. Okay? And not only that, we can find the bugs in the LLVM source code by doing this kind of compiler-assisted project, right? Because we are extensively examining the internal behavior of the compilers. Therefore, we can also help to augment the LLVM's official documentation on debugger information updates, right? Because we have more hands-on experience. So this shows one patch that we proposed, and to enhance like a debugger information update behavior in the official LLVM's documentation. Okay, so so to sum up, and by using this compiler-assisted framework, and we can advance the traditional compiler validation workflow, and we can not only find the bugs, but we can also propose patches. We can not only find the patches for LLVM source code, we can also propose patches or enhancements to improve the documentation of LLVM. Okay, so that summarizes my first application. I will pause for a second and to see if there are any questions. Okay.
Wonderful work. So I'm wondering if each of the LLVMs, like optimization paths, can be, processed individually, meaning that could it be the case that some optimization path destroys debug location or information, but some other passes that has to run after that can restore or whatever things to it? Or is that part of the things you're considering, or you're comparing, I mean, the combined effect of all passes, like, and then you derive the expected behavior from that?
Yeah. So in our existing work, we are not instrumenting each individual optimization path. We are instrumenting the debugger like a class in LLVM. Okay. Therefore, for whatever individual optimization passes, as long as it calls the debugger like a class or instruction class, and we will always be able to record that. Therefore, we will have a trace. Right. Basically, in this work, we don't care about each individual optimization path. We just collect the trace of the updating actions taken to optimize our program, and then we use the trace to establish the mapping, as well as get to know what compiler does to update the debugger information.
Got it. Thank you.
Okay.
I got another question. I was wondering whether the reordering of instructions, or even when the program is executed on a out-of-order CPU, would that affect the debug information location?
No. This is like a the compiler is only performing static analysis. Okay, so it has nothing to do with the runtime behavior of the program. So we are dealing with the instructions in the assembly, in the binary code, right? We don't actually, we actually run the program, but the instruction reordering corresponds to traditional static analysis, where for example, for some people optimization, right? You want to kind of optimize a sequence of instructions to one instruction, and sometimes you need to reorder instructions in order to maybe resolve the dependencies. It has nothing to do with the out-of-order execution on modern CPUs, because that's a dynamic behavior. So right now we are dealing with the sequence of instruction in the binary code. It has nothing to do with the runtime behavior of the program. Yeah. Okay. So.
Great talk. If I perceive the approach correctly, it first extracts the update trace of the compiler, and then implement a golden model about how the debug information should be updated, and compare your implemented golden model with the original compiler's behavior.
Yeah.
If something mismatch, there must be a mistake in the original compiler or in my golden model implementation. So how do I know the bug is in the compiler or in my own golden model implementation of this debug location updating process?
So our ground truth, our golden model, is based on those three rules, and those rules are extracted from the existing LLVM documentation. So as long as we prove the correctness of these rules, and we can be certain that the ground truth is correct.
But from an engineering point of view, you may also have bug in implementing those rules. Yeah.
I think you raised a very good point. Okay. Mm-hmm. So basically, bugs can occur in any places. Like even for this reporting mechanism, your reporting mechanism could also be wrong, right? Maybe there's a bug in a print statement or whatever, right? Therefore, for example, it could be the case where compiler performs A, but it reports that it does B, right? It's also possible. And in our static analysis, because we need to traverse the internal structure of the control flow graph of internal LLVM data structure to obtain the control flow information, the traversal itself can also contain bugs, right? So yeah, I think what you are mentioning is kind of a more fine-grained view on the internal behavior of the compilers. If there is a discrepancy, we need to examine the entire situation more carefully. So yes, I agree with you. It's not always the case that our golden implementation is always correct. But according to the rule, first of all, the rules are correct. But the LLVM implementation could be wrong. Okay. But according to our experience, it really happens, meaning that the compiler's logic could be wrong, but usually the compiler will be honest to tell, like if you do the instrumentation carefully, the compiler will always honestly tell you what it does.
Okay.
Yes, that's our assumption, but it could be wrong. Yes.
Okay, thank you.
I have a follow-up question. So, the same compiler, they generate different optimizations and code for different architectures, right? So, for your approach, does it consider different architectures or?
So what we do here is like a it's like the middle end, like a machine independent optimization, because like this is like a compiler there are two types of compiler optimization. One is the like a compiler machine independent optimization, like a data flow analysis. The other is like instruction selection, right? So in this case, this debug information update business is usually in the middle end, meaning that they are doing like it has nothing to do with the underlying like the machine dependent optimization. Okay. Oh, so many questions. I have one more application to discuss.
Hi, I think your technique is really cool. I'm curious about the current state of support for floating point optimizations. Like if I deliberately do something to approximate the result to trade for performance, can you quantify like how much the optimization hurts the accuracy?
Actually, our work is based on like our work doesn't focus on specific data type or semantics, right? So we only focus on in this work we only focus on debugger location, right? Like whether or not the debugger can stop at a certain location. Therefore, whether or not the program contains floating point operations or integer operations, it's not. We are not validating the correctness of the program. We are only validating the location, debugger location information. Yeah. Okay. All right. So this will probably wrap up the first application, which is more concrete. So next, I'm gonna talk about a work in progress. So this one is less concrete. So I will be introducing the basic idea to speed up the state-of-the-art SMT-based translation validation tool, which is LLVM. Okay, so we know that translation validation basically focus on, right, unlike the debugging information generation, right, translation validation focus on proving that the two programs, right, original program and optimized programs are equivalent. Okay, so we achieved the equivalence proving goal by using some external solvers. Like we can first model the semantics of the input program using SMT constraints, and we model the behavior of the optimized program using SMT constraints, and then we just add some quantifiers to prove that the two programs are equivalent. This is the state-of-the-art approach for translation validation implemented in LLVM. Okay. The problem with this is scalability. So if your program is too complex, for example, if your program contains loops, okay, so then you have to use some heuristics to unroll the program into some depths in order to do this SMT-based reasoning. Or if your program is like a real-world program, like HTTP server or something, right? Then you need to basically encode HTTP whatever request in SMT, which is very challenging. Therefore, this SMT-based approach currently hasn't yet been able to scale to real-world applications. And we want to use compiler-based analysis to further improve the scalability of the SMT-based translation validation tools. That's the goal of our approach. Okay? So the technical insight is that we noticed that in this SMT-based translation validation workflow, and we are dealing with monolithic constraints. Monolithic means that we only encode the program behavior of the original program and the optimized program. Then we try to prove that the two types of constraints are equivalent. and we can actually do better with the help of compiler information. Okay. Next, I'm going to describe 2 angles. The first angle is, I think it's more intuitive. Okay, let's take a look at this particular example where alive 2 timeouts are in this example. So we have original program P. We have original program P0, and because we are dealing with a full compiler optimization path, right? So the sequence. So the compiler will actually, there are maybe 112 optimization individual optimization passes performed on this input program. Therefore, we end up with P112. And it's not hard to imagine that a different optimization may touch different parts of your program, right? Sometimes, like for example, this insta combine, like which is a PO optimization, and then this like a scalar, like a replacement, pass performs aggressive like optimization on this particular example. For some other passes, like those passes, it rarely touches the any part of the code. Okay, so in a traditional SMT-based compiler validation, translation validation approach, we will encode the behavior of P0 using SMT constraints, and then we will encode the behavior of the optimized program P112 using SMT constraints, and then prove that 2 programs are equivalent. The problem is that P112, where's my cursor? Okay, yeah. So after the optimization sequence, P112 may look significantly different than P0, right? Maybe it does some like radius allocation or so on and so forth, and it will, actually those are IRs, so it will not perform radius allocation, but it will perform some aggressive optimizations, right? Therefore, the final program will look very different from the original program. The first idea is that by tracking the compiler internal information, we can actually find the middle point. Okay, in this case, because we can track the compiler, we can basically track the work that has been performed in order to produce the next program. So we can use heuristics to find the middle point, which is a P28. Okay, arguably, compared to the final program, P28 will look a little bit more similar to the original program, right? If the 2 programs look similar to each other, then the SMT constraints emitted from these 2 programs will also be similar, to each other. Therefore, the SMT solvers will be able to maybe eliminate some redundant constraints in order to prove it. This is exactly the case here. If we find out the middle point, 28, and then we encode 3 programs using SMT constraints, first, we prove the equivalence between P0 and P28. The SMT solver is able to give us a result in like roughly 400 seconds. And then we encode the P112 using SMT constraints, and then use the solver to prove the equivalence between P28 and the P112. And then the SMT solver is able to give us a result on 100 seconds. By doing that, we can prove that the equivalence between P0 and the P112. Okay, so this is what we call temporal decomposition. So in the entire compiler optimization sequence, we want to instrument the compilers and then know the kind of code that has been changed with respect to each analysis pass, and then we use some heuristics to find the so-called middle points. Therefore, we can break down monolithic SMT constraints into some simpler parts in order to achieve the validation. Okay, this is one angle. Okay, the other angle is that so here we are looking at the horizon of the entire optimization sequence. Even for a single optimization path, sometimes the SMT-based approach may still run out of time on a single analysis path. Here is an example. So here there is no sequence, right? So it corresponds to only one optimization path. So the optimization path only changed the code described in the 3 boxes. It does not touch the white areas. Okay. The traditional SNT-based approach will encode the entire program using SNT constraints and the output program using SNT constraints and then prove that they are equivalent. The challenge in this particular example is that if you take a look at the unchanged code, it corresponds to memory load and store. Okay, memory load and store are super expensive to be modeled in SNT constraints because it doesn't have a pointer like a theory in SMT solvers. Therefore, with the memory load and store, the solver will time out on this particular case. But here we know that in this case, we know that by instrumenting compiler, we know the compiler does not even touch the white part, right? So in our approach, basically by instrumenting compiler, we can generate a new program where we can omit the untouched parts. Okay, of course, here we need to do some data dependency analysis and to include some necessary instructions and to construct this program. Okay, so we decompose this program by. Where's my cursor? Okay. Okay, yeah. So decompose this program into a smaller program, and then for the optimized program, we can also decompose it into another smaller program, and then we kind of use SNT-based approach to prove the equivalence between these two, like changed programs. That will dramatically simplify the complexity of SMT constraints generated in this case. In this case, the SMT solver is able to prove the equivalence between these two programs in roughly 7 seconds. Okay, so to sum up, and I briefly mentioned the two angles to improve the traditional SMT-based translation validation tool. The first one is what we call temporal decomposition, meaning that we kind of instrument the compiler and then find the right middle points. Therefore, like in our motivating example, originally alive2 times out on the benchmark program, but by doing the temporal decomposition, and the alive2 is able to produce a result in roughly 10 minutes, and we can also combine, right? We can also combine the like in the spatial and the temporal decomposition, right? Because spatial only focus on one pass, and the temporal focus on a sequence of passes. We can combine both, and then we can basically achieve better result. So this slide shows what we do and how the compiler optimization, compiler instrumentation can help, right? For the spatial angle, we can track the optimization source code, okay, LLVM's optimization source code, and we can exactly know what part of the program has been changed. And instead of encoding the entire program, we only encoded the gray parts, I mean the changed parts into SMT constraints, and then to prove they are equivalent. And for the other temporal angle, and by tracking the compiler information, we can track the amount of code that have been changed by each optimization path, and then we can find the middle points to basically to facilitate the translation validation. Okay, so this slide shows some preliminary results, and we compare our approach against the two modes in alive2. Basically, alive2 has two modes. One is called end-to-end. It is like where's my cursor? Okay, end-to-end. Basically, it's a beginning and end, and pass by pass. Like after running each optimization pass, we run alive2 and to prove that equivalence. So our approach can basically kind of speed up the translation SMT-based translation validation by roughly two times. And our approach is especially useful when the program is bigger. Okay, so for those bigger programs, and like in this case, we can achieve like a 2.4 speed up compared to the both the pass by pass and end-to-end results. Okay, and we can also solve some problems. We can also prove certain cases where cannot be proved by the original default like setting in alive2. Okay, so this concludes my my discussion on the second application. Okay, to sum up, hopefully in this talk I have convinced you that it is beneficial to analyze the compiler internal like traces, and by utilizing the traces, we simplify the analysis problem. Recall that without the trace, we are trying to prove in the equivalence of the input program and output program, which is a hard static analysis problem. But once we have the trace, we know what the compiler does to produce the output program. The problem is simpler, okay? And there are also a few future directions. And for example, we can look at more applications, and we can also define the semantics of the traces. Therefore, I think our end goal is to develop a eBPF type of framework for compilers. So we have an eBPF for Linux kernel, right, which is very useful to analyze programs. And we also want to design such a mechanism for compilers. Therefore, when the compiler optimizes the code, I get a trace and I can analyze the trace. Okay, and on the other hand, there might be some interesting theoretical problems to consider. For example, consider a compiler optimization path. Is it possible to obtain some minimal observable events, and in order to tell that the optimization is correct? So yeah, so I believe that this is a fruitful area, and a lot of exciting things can be done just by instrumenting a compiler. Okay, that will conclude my talk on compiler-based translation validation. And thank you, and I would be happy to answer any questions. Thank you.
Thank you, our keynote speaker. Any questions?
Yes, that's great. And I have a small question. Maybe it's already your future direction. So previously, when you are showing an example, you have 3 areas that is modified by a compiler, by an LLVM path, right? And you make a new code fragment, combining all of them. And you say you verify in this small code fragment to speed up.
Yes.
My question is, can you maybe just verify in the blue one to blue one, green one to green one, yellow one to yellow one?
Yeah, that's basically, so that's a good idea, but we need to decide case by case. Like in this case, when you generate, say if you only generate a program with respect to the blue or purple box, sometimes the compiler will reorder instructions. In this case, maybe it's feasible to do that. But in order to generalize it to a general framework, we need to do more aggressive static analysis and to show that, okay, basically the box corresponds to consecutive instructions, both in the original code and optimized code. Okay, only then can we prove that, can we adopt this kind of partial decomposition idea.
I see. So, but if you can have this mapping, the blue one, and so you have 2 blue one on the left and right, and you have green one on the left and right, you already have this mapping. Even they do some maybe code reordering, maybe you can just change.
We also need to do some side effect analysis. The code may also change some part of the some other states in a program. Therefore, yeah, I think it's useful, but it requires more sophisticated analysis.
I see. Yeah. Thank you for answering.
About the same slide, right? Maybe following up on Chenyo's question over there. So we started with the job of translation validation. Is the original code equivalent to the transformed code?
Yeah.
And now, to be able to trust translation validation, I also need to trust that you or your students have implemented the spatial decomposition correctly. So does this mean that we need compiler validation?
So that's a good point. So basically, there are 2 kind of threats to validity, right? First of all is that I think one student also mentioned, how do we trust the compiler reported the right thing? Second is that how do we trust that we produce this correct program, okay? So there are 2 cases. If our program can prove that they are equivalent, chances are that they are very likely to be equivalent, because in order for it to be wrong, and one part needs to cancel out the error, right? Suppose that there are several parts and each part are incorrect, right? In order to achieve the final equivalent result, and one part needs to cancel out, right? One mistake needs to cancel out the other mistake, which is very unlikely, okay? On the other hand, if we cannot prove that the two programs are equivalent, okay, then we can take a deep dive into why it is inequivalent, right? So it could be the case where the original program, these two programs are equivalent, but somehow our implementation is incorrect. Therefore, I think, so yeah, there's no guarantee that like most of work, right? There's no guarantee that we have implemented the right thing. But in terms of compiler validation, and we can also basically, for any inequivalent result, we still need to analyze what exactly the problem is by tracing. I mean, therefore the trace comes in handy, right? So we can trace the actions taken in the compilers, and then to kind of further diagnose the issue.
Thank you for the talk. I have two related questions about temporal decomposition. The first question is, I may miss the detail, but I wonder what's the criteria for deciding that checkpoint using the compiler traces. And the second related question is whether we can insert multiple checkpoints in between to further accelerate the validation process.
Yeah, so this is still in work in progress. I believe what we have done in this example is that we actually changed the amount of code, that is the amount of the number of instructions that have been changed in this optimization pipeline, and then we find the middle point. But as you mentioned, there doesn't need to be one, like the entire process should be iterative, right? Like if we find one cut point and we cannot solve it, then we may want to find two, we might have three, and it's like iterative process. There's no guarantee that this 28 will always work.
Okay, thank you.
Okay.
No questions? I can have one question. So continue for your second approach. You want to validate part of the code. It's the next slide. Yeah, right, here. How can you guarantee that? Because you need to connect the blue part to the gray. How can you guarantee that your generated code is?
We need to do data dependency analysis.
Okay.
Yeah, we need to do the data dependency analysis connecting these two disconnected parts. And if if there's intermediate variables used across boundaries, and we need to include those instructions and variables as well.
Cool. So you only remove those variables not involved in iSQL?
Yes.
Okay. Any other questions? It's almost last one. Okay.
I've got one non-scientific question. A non-scientific question.
Non-scientific. Okay.
I think it would take a long time for a researcher to inspect the trace, since this is a testing-based methodology. And when I have an input program for the compiler to compile to an optimized program, and I observe there's a difference between the compiler trace and my implemented golden version of my implemented interpretation of this trace, and I need to figure out whether there's something wrong with the LLVM compiler or whether there's something wrong with my implementation.
Yeah.
I'm wondering how much time it takes for a student to figure out one program if what's going wrong. Yeah,
I believe my students are using LLVM to help this process, which is very handy, very useful. Use LLVM. Yes.
LLVM. Okay. No, without okay.
Yeah. So at the end of the day, you still need to manually verify whatever result you produce.
So I'm just curious about the labor, the level of labor intensity involved in this process. It's just out of pure curiosity.
Okay. I think we talk offline.
Okay.
Yeah. Thank you.
Well, thank you, Qirun, for this inspiring talk. And thank you. And the next, we are going to have our regular presentations, paper presentations.